Welcome to this session on functional safety and risk management for biogas installations. In this presentation, we will explain how HAZOP studies, SIL assessments, and safety critical elements work together to identify, evaluate, and control major hazards in biogas facilities. Detailed examples, case studies, and quizzes are covered in the full functional safety training program. This session provides an overview of the key concepts and methodologies. As biogas plants grow in scale and complexity, a structured approach to hazard identification, risk assessment, and safeguard management becomes essential to maintaining safe and reliable operations. The concepts presented in this session can be tailored to specific facilities through workshops, practical exercises, and site-based coaching. Our objective is to transform process safety principles into practical actions that improve safety, reliability, and operational performance. By the end of this session, participants should understand the key principles linking hazard analysis and functional safety in biogas installations. We will begin by reviewing the purpose of a HAZOP study and how it is used to identify deviations from intended operation. We will then examine how HAZOP results provide the foundation for SIL assessments and the specification of instrumented safeguards. You will also learn the difference between preventive safeguards and protective safeguards, and understand the terminology associated with safety critical elements, safety instrumented systems, safety instrumented functions, and safety integrity levels. Finally, we will apply these concepts to typical biogas process areas. Before discussing hazards and safeguards, it is important to understand the scope of a typical biogas facility. The process generally begins with feedstock storage and preparation, followed by feeding systems and conditioning tanks. Material is then processed through hydrolysis and digestion stages, where biogas is generated. Downstream systems may include gas storage, gas treatment, biomethane upgrading, carbon dioxide recovery, grid injection units, combined heat and power systems, boilers, and in some cases methanation and high-pressure compression. Each process area contains different hazards and operational challenges. As a result, hazard studies and safety analyses must consider the entire process chain rather than focusing on individual equipment items. Biogas installations present several significant process safety hazards. One of the primary concerns is the release of methane, which can create flammable or explosive atmospheres under the right conditions. Hydrogen sulfide is another major hazard due to its toxicity. Even relatively small releases can present serious risks to personnel. Mechanical risks also arise from overpressure and underpressure conditions in tanks, vessels, and gas systems. These events can damage equipment and potentially lead to loss of containment. Operational problems such as overfilling, blocked outlets, failed instruments, and abnormal liquid levels can initiate hazardous scenarios. Understanding these hazards is the first step toward selecting effective safeguards and managing risk. HAZOP stands for Hazard and Operability Study. It is a structured and systematic review performed by a multidisciplinary team to identify how a process can deviate from its design intent. The method uses guide words and process parameters to stimulate discussion and uncover credible scenarios that may lead to hazardous events or operational difficulties. In addition to identifying hazards, HAZOP also examines operability, maintainability, and plant availability issues. The outcome is a series of recommendations aimed at preventing incidents, improving reliability, and ensuring that risks are reduced to an acceptable level. HAZOP study is normally divided into nodes. A node represents a section of the process with a defined design intention. The team applies guide words such as no, more, less, reverse, part of, and other than to process parameters like flow, pressure, temperature, level, and composition. For example, the guide word no flow may prompt the team to investigate causes such as pump failure or valve closure. The team then evaluates the consequences and existing safeguards. This structured approach ensures that deviations are assessed systematically, rather than relying solely on personal experience or intuition. The methodology helps reveal hazards that may otherwise be overlooked. The results of a HAZOP study are documented in detailed worksheets. For each deviation, the team records possible causes, potential consequences, existing safeguards, and any additional recommendations. Safeguards are often classified as preventive barriers that reduce the likelihood of an event, or protective barriers that reduce the severity of consequences after an event occurs. The HAZOP team may identify situations where current safeguards are insufficient and recommend additional actions. In some scenarios, the study may conclude that an instrumented safeguard requires formal SIL assessment. This creates the direct link between HAZOP and functional safety activities. SIL stands for Safety Integrity Level. It is a measure used to define the required reliability of a safety instrumented function. SIL levels range from SIL 1 to SIL 4, with SIL 4 representing the highest level of integrity and the lowest probability of failure on demand. The purpose of a SIL assessment is to determine how dependable an instrumented safeguard must be in order to achieve an acceptable level of risk reduction. In practice, most biogas applications involve SIL 1 or SIL 2 requirements, although the final determination depends entirely on the assessed risk. HAZOP and SIL are complementary activities within the overall risk management process. The HAZOP study identifies hazardous scenarios, their causes, and their consequences. When the risk cannot be adequately controlled using existing safeguards, a safety instrumented function may be required. The SIL assessment then evaluates the risk and determines the reliability required for that function. In simple terms, HAZOP identifies what can go wrong, while SIL determines how reliable a critical instrumented safeguard must be to prevent or mitigate the hazardous event. Without HAZOP, there is no clear basis for defining the required safety functions. One common approach to SIL determination uses a risk graph. The assessment considers 4 key parameters. The first is consequence severity, which looks at the potential impact on people, the environment, and assets. The second is exposure frequency, which considers how often personnel are present in the hazardous area. The third parameter is the possibility of avoiding the consequences should the event occur. The final parameter is the likelihood of the initiating event or unwanted occurrence. Together, these factors help determine the amount of risk reduction required, and therefore the target SIL for the safety instrumented function. Safety critical systems are systems or functions that play an essential role in preventing major accidents or mitigating their consequences. Examples include pressure relief systems, emergency shutdown systems, fire and gas detection systems, and safety instrumented systems. Interlocks, permissives, trip functions, and certain alarm-based operator responses may also be considered safety critical when they are relied upon for risk reduction. Once identified, these systems require appropriate performance standards, maintenance, testing, and management throughout their life cycle. The objective is to ensure that the barriers identified during risk assessments remain effective whenever a hazardous situation develops. The ADEPP workspaces provide a structured learning environment for process safety professionals. These workspaces contain technical standards, procedures, lessons learned, templates, and engineering guidance covering a wide range of disciplines. Topics include HAZOP, SIL allocation and verification, safety critical elements, fire protection, hazardous area classification, drainage systems, plant layout, emergency response, and reliability engineering. The goal is to support both competency development and project execution by providing easy access to validated technical knowledge. Participants can progress through learning paths at their own pace while benefiting from industry best practices. The Biogas ADEPP AI Coach has been developed specifically to support professionals working in the biogas sector. It assists operators, engineers, supervisors, and managers with process safety, risk assessment, hazard identification, and operational improvement activities. Using recognized methodologies such as HAZOP, the coach helps users evaluate process deviations, identify causes and consequences, assess safeguards, and generate recommendations. The system covers a broad range of biogas assets, including digesters, storage systems, upgrading facilities, compressors, flares, combined heat and power units, and utilities. Its objective is to provide practical guidance that improves safety, reliability, and operational performance. In this session, we reviewed the relationship between HAZOP studies, SIL assessments, safety instrumented systems, and safety critical elements within biogas installations. These tools provide a structured framework for identifying hazards, evaluating risks, and ensuring that critical safeguards are capable of performing their intended functions. ADEPP training workspaces and the ADEPP AI Coach are designed to support organizations in strengthening process safety, competence development, and management of change activities. If you would like additional information, customized training, workshops, or coaching support, please contact us at admin@epc365.com or visit our website at iatech365.com. Thank you for your attention, and I wish you continued success in your process safety journey.